this colloquium series. Thank you all for coming. So just a small disclaimer, I will not be able to say anything very new on this topic, but my feeling is that so it's a fascinating topic that has maybe lost some of its momentum because there were not too many new results in recent years, but also since, as you will maybe see in the talk, many of the key players of its history are present here at the IAS. So I thought that it would be a good idea to maybe warm up some of the topic. And also to some, if you know the story of Morrey's conjecture, I apologize, it may be a little bit, you will not hear much new. Okay, so what's Morrey's conjecture? So basically, the question Morrey was working on in the 1950s is what is the right notion of convexity in the calculus of variations. So the integral in the simplest form is something like this, where that we're looking for its minimum over mappings from some domain in Rn to Rm, and mostly, okay, the question is mostly interesting if m is bigger than 1, and maybe plus boundary conditions. So this is the variational problem, and the question is, what is the sort of convexity type condition on F? So I'm ignoring other properties like growth conditions and smoothness. I'm just focusing on the convexity condition on F that guarantees that this is a well-posed variational problem. So the kind of ellipticity notion. And so more precisely, the question was about the lower semi-continuity of the integrand. And what Morrey proved is that so this integral is weakly lower semi-continuous, which is basically the right notion. And let's say that's ellipticity if and only if F is quasi-convex, which means the following. So if you take the integral of f of some matrix A plus a perturbation minus f of A, x, this should be bigger than or equal to 0 for any matrix A. So now this, you see this f, so U is mapped from Rn to Rm, so du, total derivative is an m by n matrix, so this f is a function on matrices, either all or some subset of matrices, and so this inequality should hold for all A and all compactly supported perturbations. So saying it somewhat geometrically just means that affine maps should be minimizers subject to their own boundary conditions. And if you're more geometrically minded, even then you can say, so there's an analogous condition in
the boundary conditions in the perturbation in U or something like that.
This is, sorry, it's compactly supported.
Compactly supported.
So you can say, so I vary the constant map. So here's the constant, sorry, linear map with some, they should have the same boundary conditions. And this inequality just says that this one should have lower energy.
And A is constant.
A is constant. A is a fixed constant. Yes. Okay. So that's just so that's a nice condition. This is a wonderful result, but it's something that's difficult to check. So if I give you a function on matrices and ask you, is it quasi-convex? It's an implicit definition. It's a property of it, but how to check it? And Morrey asked the question: is there a local condition? can I take derivatives, evaluate some derivatives of f, like convexity is something you can do that way, and that guarantees, get some condition that guarantees that this is true. And okay, so of course, if f is convex, then this is true. Then it is true that f is, I'll just write QC for quasi-convex, but the converse in this vectorial case, if m is, I'll just say m is at least 2, the converse is not true. You can, for instance, take f of a equals the determinant of a. So then actually the integral is identically equal to 0. The integral of the determinant the determinant of the Jacobian matrix does not depend, just only depend on the boundary conditions. Okay, and more generally, you could take some convex function g of a and its determinant. So something like determinant a squared plus a squared, something like this. So any convex function where you think of this that a as a new variable. And of course, more generally, you can take any minor of a. For instance, if it's not a square matrix.
The condition doesn't depend on omega.
Yes, so that's something that I believe Morrey proved, that this condition doesn't depend on omega. Exactly. You should assume that the boundary is maybe not too bad. It should have 0 measure. Okay, and so these examples, convex function of the matrix and its subdeterminants, are called polyconvex. I'll just continue here. F convex implies quasi-convex, but so these are called polyconvex. And of course, it's a more general class. And this class of functions was introduced by John Ball in 1977. They play a role in nonlinear elasticity, which is a typical field of application of such problems. And okay, on the other hand, you may ask, what condition does quasi-convexity imply? And so that's easy to play around with this implication, because you can just take a particular class of perturbations and just see what that gives you. And if you take planar maps, so these are maps that just depend on one direction in Rn. So they're not compactly supported, but you can kind of cut off on the boundaries. That doesn't really matter. The point is that planar maps will have rank 1 gradient. So then F will be rank 1 convex. Which means that if you restrict F to a rank 1 direction of this form, then this is convex. So this would be the rank 1 matrix, which is the derivative of the map A times the sine x dot xi. Okay, and so polyconvexity implies quasi-convexity, and this implies that F is rank 1 convex. And so somehow this question of whether there is a local condition is essentially reduced to the question whether, if F is rank 1 convex, is it quasi-convex? That's the, nowadays, that's what people call Morrey's conjecture. Does rank 1 convexity imply quasi-convexity? Okay, and so there are number of, of course, if m is equal to 1, so what do we know? If m is equal to 1, then everything, all of these notions reduce to convexity in the scalar case. You just have convexity.
Does rank of convex mean it's all like the epsilon, like the direction is fixed, like
For any, so this is true for any A and any psi.
Ah, okay.
So take any rank 1 direction, it should be convex along that direction. But for instance, you can take the determinant that has that property, but it's not convex. Okay, and so everything reduces to convexity, and if M is at least 3, then the answer is no. This is a famous example of László 92. Okay, so you might say, well, I mean, essentially it's done, the question, right? You know, we have, I mean, there's M equals 2, but okay, I mean, most of the cases are known, so what's the big deal? But it turns out that the M equals 2 case is somehow the most interesting one. Maybe it's because we say it's most interesting because that's the one that's open. I should have said, so M equals 2 is open, but it's the one that has a lot of connections to other fields.
Is counter construction something easy to state or easy to show?
I will talk about it. I will talk about it. So I will focus from now on this M equals 2 case, and more precisely, so focus on the 2 by 2 case. So also the domain is 2-dimensional. Okay, but I will mention this counterexample. Explain more or less how it is. It's very simple. Okay, so why are people interested in this 2 by 2 case? Okay, so implications, let's say. Implications of this, if the answer was positive, let's say. Rank 1 convexity did imply quasi-convexity in the 2 by 2 case. I would say probably the most well-known or most popular implication is that it gives sharp constants in various problems, and the most prominent one is for the AP operator norm of the Erling R-force transform. So P is the Erling R-force transform on the plane, which is a, so this is a Calderon-Zygmunt operator and has a symbol which is psi bar divided by psi. And so it has the property that if you apply it to the z bar derivative of a complex function, it gives you the z derivative. Okay, and because of this property, it's the most important singular integral operator in planar analysis. Okay, so it's important for quasi-conformal maps. It's important for equation.
Values of P.
Sorry?
P between 1 and infinite. What P?
Well, it's not known for any P.
You're saying if that conjecture is true.
Oh, so if the conjecture is true, then the P would be P minus 1 if P is bigger than or equal to 2, and P prime minus 1, the Herder dual, if P is less than 2. That would be the conjecture. Okay. And that's sorry, 2 things. So if this is true, then we know that. This is a separate conjecture, which was made by Ivanets in the 1980s. And there's very strong indications that this is true. I don't think anybody believes that this could not be true.
This would be Ivanet's twin brother. Ivanet's twin brother.
The twin brother, yes. Twin, difficult to distinguish.
In New Jersey.
For us, it's the other way.
I know, right?
For us, it's the only one. It's the big brother.
Exactly.
Ours means New Jersey.
Okay, so just to give you an idea of how this implication implies that, let me just look at the following very simple example. So this is motivated by Burkholder's work in the 1980s. So take the Haar basis on R and consider two functions with Haar basis decomposition, Fk and Gk. Okay, such that the norm of Fk equals the norm of Gk. It's the same norm of the coefficients. So they don't have to be scalar value. This could be functions from the real line to some Hilbert space. And so of course the statement of Burkholder is much more general, but I just want to go quickly.
FK is a number.
Sorry?
That's a Fourier, that's an expansion. FK is a number.
They are values in a Hilbert space. Fk and Gk are values in a Hilbert space. The Hk are scalar numbers.
Okay.
It's a Fourier expansion, but with values in Hilbert.
So what's a Haar expansion? Sorry, what's a Haar basis?
Haar basis is the dyadic basis where you have this from 0 to 1, 1/2, and you have +1, -1, and then you take a dyadic version of this, and what else do you need to do? So it's an orthonormal basis of L2, where
Okay. So the HKs are functions, are orthonormal functions.
on R in L2.
Okay, thank you.
And they have the stronger property, I mean, like Fourier, but they have the stronger property that which is important, is that if I take any function of, say, the first n of them, multiply it with the n plus first, and this is 0, because they live on different scales. They're constant on dyadic scales of different sizes. Okay, is that okay? And that's actually so that's important. But so the statement of Burkholder, let me first state that, is that the LP norm of G is bounded by p-1 times the LP norm of F. And again, it's the same. So let me just concentrate on the case p bigger than or equal to 2. For p less than 2, it's the dual. Okay, and the proof of this inequality. So you might say, well, so it's sort of like I'm doing something like that with the Hilbert transform, because I'm multiplying the Fourier coefficients by number of modulus 1, which is what I'm doing here. And so I get the same norm, but so the proof here is the following. Just a quick, so Burkholder introduces the following function of what did I want to? Okay, so this is a function of h times h r defined. Actually, let me just skip the definition of the function. Let me just say two properties of it. The first one is that it's less than or equal to p-1 to the power p, z to the power p, w to the power p. Okay, and the second property is that it has a certain convexity property. So if I restrict this function to a line where the modulus of z is the same as the modulus of the w tilde, then this is convex. Okay, and so now if you take a sort of partial sum of f and g and plug in say fn, so n plus 1, gn plus 1. Then you can use this convexity property to get back to Fn Gn because they have the same norm. The difference is have the same norm. So this is bigger than or equal to what we have with Fn Gn plus the derivative, which is some function. We did not worry about that, depending on Fn Gn times Fn plus 1 Gn plus 1 times Hn plus 1. Okay. Sorry about the bad usage of the board. And so you see, it's exactly this property that will tell me that this term is 0. So you have a monotonically increasing sequence, and that will give us that the integral of f g is non-negative. And you just plug in this pointwise inequality and get the result.
Sorry, what was PP? You just chose P. What was P?
There is a definition. It's a formula. It's not very complicated. You can write it down, but it doesn't really help.
But we care about only that property.
Yeah. So there is such a phi p with these two problems.
I'm sorry, what was psi? You said it, I missed it. The other function you said had integrals.
Oh, well, it's essentially the gradient.
Okay.
Frechet derivative.
That's the definition.
Yeah. Well, it's one property of the convexity that the second order term is positive, and one way to say it is that if you take the graph lies above the linearization.
Right, so you're just using the
I'm just using the convexity.
just using the thing that, okay, very good.
I'm just using the convexity. It doesn't even have to be differentiable. You just need to have a sub differential. Okay.
But you're missing something.
Am I missing something?
Well, it seems like it's a proof, no, but it's still a conjecture. Or
Well, no. This is a theorem.
this is.
I mean, Berkoller. This one is a theorem of
But
Berkoller.
how does it link to the other one?
Right. I'm going to explain that.
Okay.
So the link to this here is that if I consider now this setting with H being the complex plane, then so here I'm looking at 2 by 2 matrices, and so if I have a 2 by 2 matrix A, I can identify that in a natural way with C times C. Let me call it A plus A minus. So for the matrix A corresponds to a pair of complex numbers by the definition that its action on a 2 vector is the complex multiplication with Z and the complex multiplication with Z bar. So this would be the conformal projection of A, and this is the anticonformal. Okay. And so if I have a 2 by 2 derivative, then I have, okay, so this would be Z derivative of U and the Z bar derivative of U. Okay. So what is important is that the determinant of A is equal to the modulus of A plus minus the modulus of A minus. So determinant equals 0, which is exactly rank 1, when the moduluses are equal. So now you might say, well, if I would have not the Fourier decomposition of U, but a Haar basis decomposition, and this would be a multiplier of the Haar basis, this would imply my result. The Fourier doesn't work like that because I don't have something like this. On the other hand, this condition that this phi p is convex along such lines is then precisely equivalent to being rank 1 convex. So this phi p, if I restrict it to, if I just apply it to 2x2 matrices will be rank 1 convex. So if I knew that rank 1 convexity implies quasi-convexity, this would be the quasi-convexity inequality. I would not be able to use this proof, but I would know it by that implication. And okay, so that's the connection. Okay. So I mean, there's a lot of progress concerning this inequality. So here basically, what is important is not to know this, but just to know if we have this implication.
There aren't applications to variational problems.
Sorry?
This was an application to a LP bound for transform for a Calderon-Zygmunt operator.
Yes.
That's a linear. I would have thought that Morrey's conjecture being true would imply some calculus of variation non-linear application.
Yeah. Okay. So I will come to that. So okay, let me just skip then to other applications.
No. Do what you want to do.
Not really. You know.
I'm just. I was kind of shocked to see an application to Calderon-Zygmunt, which is interesting.
Which is interesting. Yes. So let me talk now. It's not calculus of variations, but differential inclusions. Okay, so here it's not really an application of what this would imply, but it's something that's very much related to Morrey's conjecture and where we can say more. Okay, so here I'm concerned with the inclusion of this type, where this is a compact set of 2x2 matrices, and I'm looking for U which are from R2 to R2. And I allow myself to look at Lipschitz maps, so this doesn't happen. So there could be jumps in the gradient. Okay, and the question is somehow, what is the correct notion of ellipticity? Okay. Now, if you look at first, say, smooth sets, so submanifolds of 2x2 matrices, then the natural notion, so this is I mean, you can write this inclusion as an equation, and then the natural notion of ellipticity is that, let's say, the linearization is elliptic, it's an elliptic system, and that here corresponds to the tangent space being containing no rank 1 lines. So for smooth sets, the tangent space of K contains no rank 1 lines. So that's actually, so in that case, these sets can be written as nonlinear family equations. And more more generally, even if the tangent space does contain rank 1 lines, such as if you think of the Burger's equations, the Burger's equation plus 1 strictly convex entropy. So in this case, you can also write the system as an inclusion of this type, with the K whose tangent space does contain rank 1 lines, but K itself does not contain any rank 1 connections. Okay, so it's sort of it's not elliptic in this sense. So this would be more generally the Legendre-Hadamard condition.
All right, is K allowed to depend on X or no?
Here, no. But of course, if it depends on X in a smooth way, you can extend. The question is if it just depends in a measurable way. That's more complicated. Okay, so no rank 1 connections. Okay, so the first case implies typical regularity statements like higher differentiability, and in the second case you still have compactness. So the inclusion is stable under weak convergence.
So these conditions are just to say that you don't have this rank one, that when you're acting with a function and you do this A plus du, you don't perturb with the rank one matrix.
Yeah, so here, I mean, this loss of compactness could result if you have a oscillatory sequence, and that's precisely what you could produce with the plane wave, a sequence of plane waves whose frequency goes to infinity.
But what's a rank one connection?
Okay, so this is a rank one connection. I just mean A not equal to B, both in K, such that the rank of A minus B is 1. So if you have a plane wave, I mean, if this is true, rank A minus B is 1, you can construct a plane wave with gradient A, B, A, B. If you remember Camilo's talk last semester, I was told by Helmut, you're not allowed to refer to a different series, you're allowed to refer to the same series. Okay, so this suggests somehow that ruling out these plane waves is somehow a correct notion of ellipticity. But if you look at non-smooth sets, so non-smooth case, so just say even finite, where you are allowing jumps in the gradient, then you can have, so there exists K, which consists of 5 matrices, where there are no rank one connections. So the rank of AI minus AJ is 2 for all A not equal to J. And there are still, there exist non-trivial Lipschitz maps taking all 5 gradients. The gradient takes all 5 all 5 values. Okay, so that's and it has compact support. So it's like a multi-dimensional version of a bump function. Okay, so it doesn't have rank one connections, but there is a trace of that. There's a remnant of rank one connections, in the sense that, and I don't want to explain this in detail, that the rank one convex hull, it's like a generalization of convex hull using rank one lines. Let me not go into the definition, but this is large in this type of example. Okay. Okay, so what we know about this non-smooth case is that so maybe this is also okay. So first statement is that if K contains no rank one connections and no T4 configurations. So T4 configurations are kind of 4 gradient version of this. There's a certain configuration of matrices that you can rule out. So you just have to test for pairs of matrices and quadruples of matrices to get this property. And they all involve rank one geometry. Then one has compactness. So there is compactness. So the precise statement is that if you have a sequence uniformly converging, and say uniformly Lipschitz, such that the distance of the gradients converges to K in L1, then the gradients themselves have to converge. Okay, so we cannot have higher and higher oscillations in such a sequence.
But this is only in the 2x2 case. Sorry, this is only in the 2x2 case.
This is only in the 2x2 case. Okay, so this is work with Danny Faraco. Coping with jet lag. That's all right. And okay, and the second statement is that more generally, even without any conditions, the essential gradient set. So this is the set of, the smallest closed set that has the property that du of x lies in this set for almost all x. The rank 1 convex hull has to be connected. So this looks like a weird statement, but it tells you that you cannot have large jumps in the gradient without having rank 1 lines somewhere in the process. Even though you can have something like this, but the rank 1 convex hull is connected. So it just tells you that this is the only type of configuration that you can have. Of course, you can have the opposite. You can have sets whose mappings whose gradient set does not contain rank 1 lines, like conformal maps or solutions of elliptic equations. But then, okay, the gradient set has to be connected. So this is, if you like, a weak regularity statement. If you have jumps, you have to have rank 1 lines. That is jumps along rank 1 lines. Okay, so this is where application I mean. And so I just want to mention that you cannot expect something like this in higher dimensions. So just an aside, there is a wonderful example of Ivanets, Tadeusz, Henrik, Verkota, and Vogel of a mapping from R2 to R2 times R2. Write it like this. So U has two components, F1 and F2, both mapping into R2, such that the determinant of dF1 plus determinant of dF2 equals 1 if x2 the upper half plane and u is equal to 0 if x2 is less than or equal to 0. So you can also say it this way. If you think of u as a mapping from C to C squared, then it's, if you like, pseudo-holomorphic. In the sense that the z bar derivative is equal to a complex matrix times the z derivative with norm less than 1. But of course, it's this matrix depends only measurably on the point. But so this tells you that there is no, there is no, not even in this extreme case, it's very far from having analytic continuation. And if you have a determinant constraint like this, then of course this would be disconnected. Okay. So examples like this cannot exist in the 2x2 case. For quasi-regular maps, one has analytic continuation, even in this generality, but this tells you that this is a more partial statement. Okay, so
how does this connect with the conjecture? So
yeah, so this role of sort of the rank 1 connections is a connection, and so let me now connect the two. These two implications. well, maybe I can do that first. Yeah. So for the, I mean, maybe some idea of the proof of this result. Yes. And so first there is something really, which is pretty special about the geometry of rank 1, the rank 1 structure of 2x2 matrices that gets used here. So let's say rank 1 geometry, which leads to the following statement. So if the rank 1 convex hull of a compact set of 2x2 matrices is disconnected, there's 2 components, then you can separate it with a curve in the following way. So there exists a curve, closed curve, which is elliptic in the sense that the determinant T minus gamma S is bigger than some gamma times S squared. Okay. And for all elements of the set K, the same thing holds. So determinant of A minus gamma T is bigger than gamma of A minus T squared. So it's a sort of, I mean, you can say it's kind of a little bit better than just saying the determinant of the shifted matrices is non-negative. And okay, so under this condition, if you take all A with this property, with say the strict inequality as the property, then it will have 2 components. That set will have 2 components, and K will lie in the 2 separate components. So okay, so that's a kind of geometric property of this whole picture. And but that has the following interpretation. I will give you an example of this construction in a minute. That will make it more clear. But this has two implications. So the first one is then being a solution of this inclusion is on the one hand saying that it's so u of x minus gamma t of x is quasi-regular. And if you have, say, affine boundary conditions, it's even quasi-conformal. Okay, that's just from the second condition. And so you have a whole family parameterized by T of quasi-regular maps. It's kind of like a tilting of this map U. And the second property is that you can, they're a solution of a Beltrami equation with where H also depends on the point. Okay, so this would be just measurable. You have the same, the Lipschitz property with respect to this variable. So it's an elliptic equation. Okay, and so using these two properties, one can, so they go into the proof of these two statements. The connection, okay, so now the connection, this question, the connection to Morrey's conjecture and Burkholder's construction is the following. There's a natural rank 1 convex function associated to this type of set. So this is, okay, so there is natural rank 1 convex function, which I will call F gamma. And so this is defined in the following way. So first of all, take F0 gamma of A, which is just minus the minimum over T of the determinant A minus gamma T. Okay, so this property says that K will be contained in the set where F0 gamma is non-positive or negative, and where it's negative, this set consists of two components, say U and V, and then define F gamma of A to be equal to 0 in U and F0 gamma of A otherwise. Okay, so in U it was negative, so I'm just raising it to be 0. So it's a kind of local maximum of two functions. Okay, so first of all, this F0 is going to be, it's actually polyconvex because it's the, and if I write it like this, maximum and the minus, then it's a maximum of polyconvex functions. It's polyconvex, in particular, it is rank 1 convex. And then I take the maximum of this function and the 0 function on one of the sets where it's bigger. Okay. It's a local maximum. So this, maybe now it's best to give an example of this. Here. So e.g., if gamma is just SON, SO2. So in the okay, so this is just a unit circle in the conformal plane of conformal matrices. Then this F gamma of A is just 0. A plus modulus A minus is less than or equal to 0 and is equal to A plus minus 1 modulus minus 1 squared minus A minus squared otherwise. This is bigger than 1. And okay, so this is just something you can calculate. The point is, if you take P bigger than 2 and integrate e to the, maybe I call it lambda to the P minus 1 F gamma of A divided by lambda d lambda. So I take this function and make it P homogeneous. And this is exactly equal to Burkholder's function. And so what is interesting is that not only is this F just a rank 1 convex function, it has more properties. It because of the way it's defined. So in particular, okay, so this is related to how people use this construction. Also to get partial results in for the Berling-Alfors transform. But just to give a very simple idea, so if you take, so let's take two conjugate harmonic functions. Say the unit disk. And so then you know that the gradient of U is equal to the gradient of V modulus by the Cauchy-Riemann equations. And so if I plug in to this F, say first to the F0, and now think of this A again as splitting into conformal and anticonformal parts. So you can, instead of plugging it a 2x2 matrix, you plug in two vectors. I'm going to plug in gradient U, gradient V, analogous to trying to plug in dzu and dz bar u in the Burkholder function, then this is going to be subharmonic, because this is a supremum, a maximum over determinant, which is so the determinant is just grad u minus grad v. So it's this is subharmonic and shifted by a linear function. And then you take a local maximum of that with 0. This is still subharmonic. And using this fact, so now using the mean value property for subharmonic functions, you can deduce properties on the Hilbert transform on the boundary. Okay, that's more or less the method of Picorides in the 1970s, and Rafakos, I don't remember, 97 for the Hilbert transform. And it's, I mean, very much related to what Wolberg, Nazarov, and many others did for the Berling-Alfors transform. Okay, so I mean, let's say I should finish here. So let me just say that it's not clear to me if rank one if it's this implies. If this is the correct question, of course, it's an interesting question. And I would say, if you ask me, I would say it's probably true, but for different reasons that I can explain in a different talk. But the connection to these sharp constants is probably something that's related to a different property of these functions. Probably something more related to this special construction, so these type of functions. Okay, that's it.
You have a question? I guess I'm a little confused. This theorem that you proved there highlights the rank 1 feature, and you get by just with the rank 1. So you don't need to know this converse. Is that your point?
You don't need to know what?
You brought this up as, is the converse true? That rank 1 convexity implies the whatever quality. And then you gave some applications to sharp constants in Calderon, Ziegler, tunnels. But in your problem of whatever it's called, mapping the convexity of the set K in the matrices,
I would say
you're getting by with rank 1 notions.
Yes. So I mean, this is so I do believe that this is true. This implication.
And would that then help
that
you?
one? So this, of course, these would also follow if we would know that. By, let's say, by applying this type of functions to those sets.
The point is that you do it independently.
Yeah, so that's more like a qualitative version, not quantitative. You don't get sharp constants, but you get the correct sets. That's the connection. So that's where we are now, I would say. I mean, not to say so. So concerning the sharp constant, there are quantitative estimates. I mean, I think the best bird record is something like 1.575, something like this, times this number by Banuelos and Martina.
Independent of P?
That constant is independent of P, yes.
I mean, the multiply.
Does it go through some rank 1 convexity of something, or is it completely different?
So I would say it's more related, at least philosophically, to something like this. They don't use the harmonic extension; they use the heat extension, and then it's based on they call it the Bellman function approach. But that's very closely related to some sort of special test function like this one. And the difficulty in reaching 1 times this number is that somehow all of the approaches, there's many papers here, I'm not citing most of them. They use the fact, okay, so they use a kind of scalar version. So they use so you can write P as these transforms. These are the Rees transforms, and they can separately estimate these ones. Okay, so it's like a scalar, and those ones give the correct estimate. So that's, I think this was, for instance, by Wahlberg and Nazarov. They prove these bounds for these two guys separately, and so you get 2. But then, of course, they're not independent, and then there's a lot of work in trying to lift it to this factorial case.
I'd like to thank the speaker again for very interesting.